Okay. The next method of preparation, ozonolysis ho gaya na? So this will be the fourth one. Hydration of alkynes. Do you remember what you get on hydration of alkenes?
Alcohol.
Alcohol. So one step aage, hydration of alkynes is going to get you aldehydes and ketones. So specifically, hydration of alkynes may, sorry, so only ethyne is going to give you acetaldehyde, and all other alkynes will give you only ketones. So the only aldehyde that you can get by like from alkynes would be acetaldehyde, that too specifically only from ethyne. Okay, we'll see the reason why. Let's see what the reaction is. So alkynes would be C triple bond C, and then you have hydrogen, like whatever it may be over here. On adding water, so water is HOH. So it's a very similar mechanism as what you have in hydration of alkenes. So one side of the triple bond, you have hydrogen getting added, the other side oxygen, OH getting added. The reason why you end up with aldehydes and ketones is that enol tautomerization. So you have, see, the triple bond becomes a double bond. One side you have hydrogen added, the other side you have oxygen added. Now, because of the keto-enol tautomerization, this is an unstable form for it to exist. It turns into a more stable form, which is C. The hydrogen migrates over here, so this becomes a single bond, and this becomes a double bond. Okay, so this is how you get aldehydes and ketones. Now, specifically, so if we start off with ethyne, because we have hydrogen on one side, on hydration, it'll just be hydrogens, basically all these empty bonds. So on tautomerization, end up getting CH3, C double bond O H. And any other alkyne, because of Markovnikov rule, like for example, if we take propine, on adding water, so where do you think the H will get added, on which side?
Can you repeat?
So addition of water, hydration means H gets added on one side and OH gets added on the other side, right? So which carbon will get H and which carbon will get OH?
The one which already has an H will get H.
H, yeah.
You get H here and you get OH here. So this is how you end up getting OH on the secondary carbon. The primary carbon, because it'll always have more number of hydrogens, will always get hydrogen, which is why you end up getting ketones. You'll never get an aldehyde from any other alkyne. If it's in the middle of the chain, that's pretty straightforward. It gets added in the middle of the chain. But if it's at the end of the chain, because of Markovnikov addition, always the secondary carbon will get oxygen. And when this tautomerizes, you end up getting ketone. So that is the reason only ethyne will give you acetaldehyde. All the other alkynes, you'll always get ketones.
Could you please explain the tautomerization part again?
Tautomerization is rearrangement. So enol, this particular form where you have an sp2 carbon and OH attached is an unstable form. So like resonance is what, like delocalization of electrons, right? So what happens is the oxygen pulls on these electrons. These electrons basically migrate over here, and when this lets go of hydrogen, so this hydrogen gets bonded to this particular carbon. So basically, there's a rearrangement of the bonds, and this tautomerizes into the ketone form.
So tautomerization happens only in compounds where there is resonance.
When there is scope of resonance, like where so tautomerization is the process where electrons migrate and the bonds rearrange into a more stable form. This is more stable. So because usually this particular tautomerization, because it's a rearrangement between a ketone form versus an enol form, like double bond plus OH. It's called keto-enol tautomerization, this particular one.
So only aldehydes can be obtained by this process, or only if we use ethyne.
You get aldehyde, you get only one specific aldehyde, which is acetaldehyde, when you use ethyne. Any other alkyne will give you ketone. So these are some methods we've seen where you can get both aldehydes and ketones from the same reagent. You just have to take the correct substrate, the correct reactant in the first place. Like if you take primary alcohol, uska oxidation will always get you aldehyde. Secondary alcohol will always get you ketone, but you're not changing the reagent. Like the reagent stays the same in all these cases. Now we look at preparation methods, which are exclusive to aldehydes and then exclusive to ketones. Yeah. Oh, still not. Okay. Yeah. Finish noting, then we'll look at the next.
So tautomerization. So why do we call tautomerization? It's just resonance only, right? It's just two like resonating structures. So
So
why the difference?
no. So they're not resonating structures. Like I've put in, this is unstable, this is stable, right? So resonance may, the whole electron cloud would be spread throughout. Like for example, benzene ke resonance may, you have the basic hexagon and the pi electrons are spread throughout. So there's always delocalization of electrons. So tautomerization may, most of the times it's going to exist in this particular structure, which is the more stable form, which is the more stable structure. So it is formed as this, like it is added across the triple bond. So you have the heat, like
Oh, so like resonance is like it's constantly changing, but tautomerization it's becoming that structure permanently.
Yeah.
For stability.
Yeah.
Okay. But why is the first one unstable? Like, what is the issue with the first one?
Again, that will have to go a little deeper. Something off the top of my head, like sp2 carbons are pretty electronegative. Oxygen is also pretty electronegative, right? Oxygen would be more electronegative comparatively.
Yeah.
So it's
Yeah.
going to keep like pulling on the electrons. And it also has to do with like the bond energies itself. So this is a lower energy state, it's a more stable state. This is a higher energy state.
So it will lose that H, no? Like OH wala H.
The H migrates over here. So instead of this having a double bond, it becomes sp3 hybridized. Yeah, let me put it. I didn't write it here. Yeah,
I didn't get what?
so this H basically migrates over here. Okay. Smera and Sia, you guys finished writing or still noting?
Ma'am,
Hmm?
the one that you've drawn in red and the one that you've drawn just below that is the same thing, right?
No, this is general. Like I have not put anything on either side. So this is an example, which is ethyl. This is propyne. So I have not filled up the form, like the bonds here. It's the general version of the reaction.
But if in the red one, वहाँ पे खाली है, if we put H, that will become acetaldehyde only. No?
Yeah, if you put H on both sides, acetaldehyde. If you put something else, it'll be a different. So yeah, what's important is like even though you have an ethyne, like a one ethyne or one alkyne where the triple bond is in the corner, it's always going to follow Markovnikov addition. So you can make a note somewhere. So even though it's in the corner, you still won't get an aldehyde because of Markovnikov addition. So as follows. Okay. So we're looking at preparation of aldehydes. So the first reaction in this section is called Rosenmund reduction. That's another thing. So this chapter has a lot of named reactions. So like once we're
Did you already write the heading? Sorry.
Till now, what were we doing then if this is preparation of aldehydes?
so till now is it right? Like you can get aldehydes or ketones depending on the reagent. Now these set of reactions are going to be only aldehydes, not ketones. No matter what you change, like yeah, you're going to get specifically aldehydes only from that set of reagent. And
Also, one more question about tautomerization. It'll always happen this is always going to happen that the triple bond ka ek bond is going to go with the O and then the H will be transferred there. That's always going to happen, right?
yeah,
And
like
but
no
not in
matter-
case.
so this is one way of getting. So no matter how you get, if you have enol structure, double bond and OH, this
Yeah.
will always tautomerize to a carboxylic structure.
And ketones.
That's all. Like if it's in the middle of the chain, you get ketone. If you have a hydrogen here, you end up getting an aldehyde.
But
So,
the basic mechanism is the same. Like
yeah,
third
enol
carbon.
hai to end up getting a double bond. So this is specifically you got the enol by hydration of alkenes. There are other ways of getting enol. We'll be looking at. Okay, so coming back to Rosenmund reduction, this is a preparation method from acyl chloride. And do you guys know what is the structure of acyl chloride?
CH3CO.
That is specifically acetyl chloride when you have two carbon atoms. Any acyl chloride, this is the functional group. You have
COCl.
Also, on the previous, is there a reagent or not? Sorry for interrupting, but in the previous one, is there a reagent other than H2O? Because ma'am said something like HGSO.
Yeah. Thank you for reminding. I forgot. So how the addition of water takes place is, you need there's a mixture of sulfuric acid, like a dilute sulfuric acid, the presence of mercury sulfate, HgSO4, H2SO4. Yeah, the presence of this one. Yeah. I was so focused on the addition of water part. Yeah, absolutely. This is there. Okay, so back to Rosenmund reduction. From acyl chloride, reduction hai matlab basically you substitute the chlorine with hydrogen. So source of hydrogen is direct hydrogen gas in the presence of palladium and barium sulfate. So if you don't use the barium sulfate here, you're going to have like pura hydrogenation, you're going to end up getting an alcohol. So in order to control it, because you want to retain the C double bond O, protect this, you end up poisoning the palladium with a little bit of barium sulfate. So you get C double bond O H. RCHO, aldehyde basically. Okay.
What is the reagent called?
I don't think this has a name.
No, the H2 के नीचे वाला.
So PD is palladium and you're poisoning it slightly with barium sulfate. So barium sulfate and sulfur. So usually when you use a nickel or platinum or palladium catalyst, you end up like that. That's a standard reagent for hydrogenation, right? When you have hydrogenation of alkenes, alkynes, things like that. But when you want to control that hydrogenation, you poison it a little bit, which is why you end up adding a bit of barium sulfate sulfur.
Just sulfur, like atomic sulfur.
Atomic, yeah, elemental, yeah. Like so. When metals are used as a catalyst, you use them in powdered form. So to that palladium powder, you add a little bit of barium sulfate powder and sulfur powder. That's mixture of all these three things. Okay, so for example, if I want to prepare benzaldehyde, what do I need to use? What reactant do I start with?
Benzyl chloride.
What is the name?
Benzoyl chloride.
Benzoyl chloride is right. Benzyl chloride means that CH.
Yeah, it's only Cl. No, that's chlorobenzene. What is benzyl chloride?
CH2Cl.
Same thing.
This is benzyl chloride.
Then what is chlorobenzene
Yeah.
called other than chlorobenzene?
Because usually we say like aryl halides. So by that logic, it is like haloalkanes and aryl halides is the same thing, no? So won't it just be?
No, but like again, this is specifically, I think we discussed this in the previous chapter also. Benzoyl, benzyl, aryl, these three mean different things.
Isn't it CuCl?
No, you're talking about chlorobenzene, right? So I just wrote that. One small note about this method: formaldehyde HCHO cannot be prepared by this particular method. So this is because the reactant is not stable at room temperature. So in order to prepare HCHO, you want the chloride to be HC double bond O Cl. So this particular HCOCl is not stable. Yeah. Not stable at room temperature. So when you're starting, chemical itself is not stable. If it's gonna break down, yeah, you won't be able to like undergo this whole reaction. Yeah, so this is Rosenmund reduction. So Rosenmund reduction is acyl, like hydrogenation of acyl chloride. Uh, you want to control the hydrogenation, so you add this particular poison to palladium catalyst.
Miss,
Hmm?
I don't know if it's only me, but your voice is very muffled.
No,
Ah.
it's not only.
Okay.
How's
Yeah, done writing?
No.
No, finish it.
So acetyl chloride is just वो R की जगह पे there is CH3.
Yeah. So anywhere you come across acid, like acetic acid, it means there are two carbons.
And what is quinoline? Is that also like a poison thing?
Can you spell it?
Or I don't know,
Quinoline.
QUI?
Okay. Quinoline. Yeah, that. Where did you come across quinoline?
In like poisoning wala, you mentioned like sulfur poisons barium sulfate.
Both the mixture of barium sulfate and sulfur poisons palladium. Palladium is a catalyst,
Oh.
right? So you want to reduce the effect of that catalyst so that C double bond O is protected. This does not become an alcohol. So here you add this poison. Okay. Okay. The next one.
I'm just 1 second.
Huh.
Yeah, done.
Okay. Next one would be preparation from nitriles and esters. We're grouping them because one of the reagent is the same for both. So use the same reagent in both the cases. Isme, the first one of them is a named reaction. So you have Stephen's reaction. So Stephen reaction is nitrile ka reduction. So first part of the reaction, you use a mixture of stannous chloride, SnCl2 and HCl. So this is going to reduce the nitrile, convert the triple bond into a double bond. So you get CH double bond NH. So this group of compound, when you have double bond NH, this particular type of compound, they are called imines. Again, alkanes is single bond, alkenes is double bond. Similarly, amines is when you have a single bond and then nitrogen. Imines is when you have double bond and then nitrogen. So imines on hydrolysis, acidic hydrolysis gives aldehydes. So this is Stephen's reaction. So Stephen reaction is nitrile plus stannous chloride and HCl mixture.
Can you spell that, like the name of SnCl?
This is tinca chloride, right? So Sn, this is stannous chloride. So how you have ferrous chloride, ferric chloride? For both the oxidation states, you have stannous chloride and stannic chloride. Abhi, because we're using SnCl2, lower oxidation state is इसलिए stannous chloride. So this is one reaction, call it 1. Now, there's another reagent you can use with dival H. This particular reagent can be used for both nitriles and esters. Have you come across dival H? I feel like alcohols maybe it's studied, right? You remember what is dival H?
Di.
D for di, I for
Diiode.
IOD.
no iodine involved.
Isobutyl aluminium H.
Yes.
Are you okay?
DIB. Al is aluminium. H
We
is.
did practicals also something.
Oh, you guys work with dival H. सही है. Chemically, so you have aluminium hydride, you have H and 2 isobutyl groups. Write it as IP. This is the formula. So aluminium is +3. Sorry, hydrogen. This exists in the form of hydride. H minus, and then the other 2 charges are like neutralized by isobutyl groups. Okay. Back to the reaction again for both nitriles and esters. It's the same reagent. With nitrile follows the exact same not mechanism, but exact same process where in the presence of dival H, this is first reduced to imines. Again, dival H, because of the hydride part of it, source of hydrogen, it's a reducing agent, reduced to imines. And this on hydrolysis gives you aldehyde. Okay, so key things that you need to remember is how many ever carbon atoms you start off in the nitrile. you're going to have the same number of carbon atoms here. So just that the nitrogen is replaced by double bond oxygen. So C triple bond N turns into RCHO. Okay. And with esters you have C double bond O R dash. Again, same thing, treat it with dibar H and hydrolysis. You get R C double bond OH. So the part that's attached to C double bond O, that is the part retained with the aldehyde. Almost done. Like last set of reactions for aldehydes, then we'll have ketones.
Then we are.
And then we'll go on to ketones. Ketone preparation methods. So,
Where is ester in this?
huh?
Where is ester in this?
This one? So Stephen reaction is specifically only when you use stannous chloride HCl instead of dibar H in order to reduce it to an imine. So otherwise, like the pattern of the reactions, the products that you get follows the same method. So if you use a nitrile, first reduced into imine, and then uska hydrolysis pe you get an aldehyde. Esters, again, you have reduction, and then on hydrolysis, you get an aldehyde. Okay.
Could you go there?
ठीक है.
Done.
Cool.
No, I'm not done.
Oh,
Done.
okay. Okay. The last set of reactions is for preparing aromatic aldehydes. Specifically from hydrocarbons. Okay. So इसमें first one that we'll be looking at is oxidation of benzene. Benzene, nahi, sorry, toluene. This also I feel like you guys have done this reaction before. At least the reagents you should be familiar with. So toluene on oxidation with CrO2, Cl2. Do you remember this? Have you come across this reagent before? No? So this is called chromyl chloride. So chromyl, CrO2, Cl2, chromyl chloride. So the oxidation of toluene gives, this is a slightly, you get CHO, CrOHCl2 taken twice. And this on hydrolysis, acidic hydrolysis, H2ONH plus gives aldehyde. So this is also another named reaction. So when you use specifically this particular reagent, chromyl chloride, this is called ETARD reaction. Then this is not the only oxidizing agent. Another oxidizing agent you can use in place of chromyl chloride. Same thing. Take toluene, heat it with a mixture of chromic, like you take CrO3 and CH3, CO taken twice, this thing. So this is a mixture of chromic oxide and acetic anhydride. So 27, like at between 273 to 283 Kelvin. Because you've taken acetic anhydride, the intermediate that is formed would be slightly different. You get CH, then O, CO, CH3 taken twice. And this on acetic hydrolysis, heat it a little bit, get benzaldehyde. So this is chromic oxide. This intermediate's name is, this is benzene. Sorry, no, benzaldehyde diacetate. So this is one reaction. Yes, quickly note it down because there's almost less than a minute left. Just note it down. I can take a screenshot. So ETARD reaction refers to the reaction where you use chromyl chloride only. So this is ETARD reaction. This doesn't have any name as such. It's just a different oxidizing agent you're using.